Today, I will talk about the approaches of doing the same task we did in previous lectures of taking the text and getting a vector out of this text, but with different approach. Previously, we used pure math, we used PCA, SVD, all these names to achieve the vector with some properties. And we figured out what are the difficulties, why dimensionality reduction is important. And today we will go to the other side, to the dark side. The people who are doing machine learning, they usually considering the problem in a different way. Because as for mathematics, it's important to be precise. For machine learning, it's important to be useful. If you train the model, even if it's mathematically precise, there is no need to use it in production. That's why machine learning is more, from my perspective, like the approaches, they're more practical. So let's just briefly refresh these terms because we will use them in the lecture. Who remembers what is term document metrics? So actually, yes, this is the matrix where you have rows and columns. For one dimension, you take the terms. For one dimension, you have texts or whatever documents you index. And in the intersections, there come some numbers representing either the presence of the word or some importance of the word for this text. For example, if the word is repeated multiple times, maybe the number will be bigger than for a single word. Okay, so what is a vector space model? Okay, so to rephrase, this is some kind of a model, which is, as you remember, is a generalistic model. It doesn't give you the tools. It says, let's try. It says, let's think about the texts as they can be represented with the vectors. We don't introduce the metric for distance between these texts, don't introduce the way how we obtain this kind of vectors. What we say that it can happen that vectors can work. And then we go for different approaches to fulfill the gaps in this model. What is distributive semantics? So maybe other students are here, not in the first row. Who remembers this term? Okay, so if you have some kind of context, meaning some kind of words in the text, the sentence or a phrase, if we take the word from this context, if we have two different words, but they have the similar context in overall text, maybe these words are also different, similar. In the example, President of Russia and Vladimir Putin, they usually met in the same context with some political terms. That's why they're semantically similar. Or, for example, as I mentioned, alligators and crocodiles. They usually eat people, so the context is the same, eat people, and we can say that these terms are similar. Again, distributive semantics doesn't give us the exact model how to, because it doesn't specify what is the context, and it doesn't specify how to use it for vector embedding. And here comes the idea, which is saying, okay, distributive semantics is the hypothesis about similar context, meaning that if you have some, so you can consider context as the row in the term document matrix, meaning that the word is met with other words in the text. Meaning that term document matrix is very sparse usually. So what we can do, we can try to search for latent space, which is linear, and which projects to term document matrix with some linear operations. So we say that our dimensionality is enormous, like 20,000 of dimensions is pretty big number to compare the vectors. So let's try to reduce these dimensions, but how? What should be the hypothesis? The hypothesis is the following. So maybe the number of dimensions is much smaller, but also we can say that this is a linear projection of term document matrix. And there should be a method which searches for such space. So for now it's latent. Doesn't mean that we don't know this space, but what if we try to search for it? And here comes these three abbreviations, where LSA means latent space analysis. So this is the method for searching for latent space. So for smaller dimensions than just a row of a term document matrix. So we're trying to make the matrix narrower. Okay, you remember this, the magic on the slide on the whiteboard, where I was trying to show that how we decompose the matrix into two matrices and then keep only the narrow one. Then, so how can we search for specific dimensions? We will use principal component analysis. You should be familiar with this method, saying that we're looking for orthogonal space, where the first dimension is the most important, meaning it holds the biggest variance from the data, and so on. So the next will be less important, but still, in the first dimensions, you usually keep the major part of variance of your data. And SVD as the method, singular value decomposition, is the linear algebra method, which helps you to run PCA. So it actually says center the data and run SVD, and this will be a PCA. Actually, the method, yes. Of latent space definition. I can repeat my understanding, not the definition. Sorry, it's not an exam. So again, as the vector space model, latent space say that vector space model says there should be some vectors. Okay, latent space say there should be some vectors of smaller dimensions that should be orthogonal. And like latent space stops using term words, it goes for concepts, saying that maybe what we will find out is not representable in human words, because these are some dimensions which are not mapped into words on the text. Because we have like 20,000 words and 200 concepts. These concepts are some vector representations. That's all. The axis in the multi-dimensional space. And these methods allow us to build such latent space with respect to the conditions. So it should be orthogonal, it should be of small dimensions, it should still keep the major of information. Okay. So today I will start with what's missing in LSA. So we went through this method. We consider it as working one. So if you did the home task or the lab, you should find that somehow it works. It allows you to search for documents, or at least for asparagus. And then we will go for different historical, I can say like historical approaches to vector modeling, which originated from machine learning. Okay, so what is missing for LSA? I think the significant issue of the approach you used in your lab was the following. So SVD, as any linear algebra method, will require you to have the whole matrix in the memory, or at least in the hard drive. And then you can fall in the situation when, for contemporary systems, when the numbers of documents are billions of documents, when the numbers of features are hundreds of thousands of features, you cannot fit in the single machine. So, and that leads you to invention of some different hacks and tricks how to run SVD without having the ability to run SVD on your machine. And of course, as it's like for contemporary methods, it's polynomial time, but it's not linear time, meaning that if you double your data for SVD, double your metrics, it will, I think, 4 times increase the time, computational time. No, fine. Exponential will be if I add one string, it will double my time. Polynomial means if I double my data, I will 4 times increase my time. It's not that bad. Actually, you can run SVD still. And of course, there are some tricks to work with this. And today, for tasks which are not only related to text search, for other recommendation system, we still use SVD. But we do what? We try to overcome this limitation of memory and time. And for example, Facebook a few years ago introduced the method which is actually randomized meaning that it is not exactly bringing you the actual value. So not the exact decomposition, but something which is similar to the composition. Uh, Also, there are some other methods of decomposing the matrix, or splitting the matrix into two parts. So one is narrow, another is projection, like alterating with squares. And both of these methods, I think, they have the ability to be parallelized in a distributed context. So it means that all in all, if you have a lot of data, you have the tools to work with this data in distributed context, and maybe in some streaming form. But uh, if we if we stop on SVG, we will lose the very important thing. The important thing is that SVG, as the tool for PCA, it assumes and it works with. You remember, it preserves the variance. It assumes that the data has the normal distribution along these orthogonal dimensions. And this is not always true for language, meaning that words are distributed in the different way as in the normal distribution. So some can say this is the Poisson distribution, which is closer, but still we don't know the distribution for words, but we assume that this distribution is normal. Some researchers tried to fix this, introducing, for example, Poisson OSA. So saying that I will somehow model the different distribution and bring up different vectors. And this method is more like pure mathematical. I think if you want to read it, there should be a link, but it's not here. But in Wikipedia, if you try to type PLSA, it will bring you to the text. And again, for all of these methods, you have the very big problem, which is this one, yeah, which is written on the slide. The problem is that for SVG, if you just slightly change one value in the matrix, you will end up with a completely different distribution. If you add a string, so just a new document in the collection, you need to run something different, some new decomposition for this. And of course, this stops us from using dynamically updatable indices. So of course, if we can tune the model slightly, it's okay. But if we need to recompute it, the whole model, it takes a lot of time. So yeah.
About the model issue.
The model? The model is the following. So we say that the words are somehow distributed in a multi-dimensional space. When you run PCA assumes that the data have the normal distribution along this unknown orthogonal dimensions. So this method states that we go for this assumption. And for this assumption, we got something, some result. Because if you remember that in normal distribution, the variance is computed as how? As rooted mean square error. So for bigger numbers, you can use statistics to model the hidden parameters. So for normal distribution, the average is the mean, yes, and so on. And this doesn't say that for these other distributions it is the same. So the parameters of the model, they are computed, but for normal distribution. Words are not necessarily distributed normally in this space. There can be some like long tails, like this, not the normal distribution. Okay? Mm-hmm. That's why there should be some different methods which can model other distributions. And
our methods to ignore the fact that words are distributed.
So these are, yes, they are ignoring this fact. These methods try to fix this problem. But still they require the whole data set in memory to run. Okay, so these are some problems with the approaches, and of course there should be some approach which is like simpler, but still solves the same problem. So we should switch from pure mathematics to something more practical, and maybe this is machine learning. So what is, just from the very beginning, what is the most important for neural networks? I think you all can train a simple or even a complex neural network. The methods of training are enormous. So starting from just the grid search for parameters, ending up with some gradient descent, stochastic gradient descent, batch stochastic gradient descent, other like optimization methods. which are iterative, which don't require you lots and lots of memory, and it allows you to work in a streaming context, saying that you feed the data with small bunches, and it trains the model. You run through few epochs, and you end up with some model which can be a good one. Okay, and instead of computing, this approach and all the methods I will consider today are beautiful because of this. So they allow us to get the latent space by not very memory consuming and time consuming operations. Uh, what else? It's not mentioned in the slide, but I have it in my comments. That in the paper, which the link is here, they say that first of all they significantly increased accuracy compared to other models. But this is like the quality issue. But also they say that for the architecture they proposed, it's very easy to use distributed again. So distributed learning for even terabyte data sets, they can train the neural network, which will work okay for the task. So we go for word-to-vec. Word-to-vec is ancient approach, which is still can be found in some projects. It's actually not the single architecture. This is two architectures. One of them is called skipgrams, another is called continuous bag of words. Just to have the overall idea, they are different in the following way. So instead of again computing the vector space model, they are trying to introduce the prediction of something, and the latent space is computed in the narrow level of neural network. So what is the difference? Skipgram says, I have a word. This word is usually met in some context. So Fox is a word, and the context is here. And I want to predict, so my target function will be prediction, which words are usually in my context. So what you get as a result, you get the you feed the one-hot encoding of the words, get the result, the vector, with likelihoods of meeting these words in the context. The other approach is like vice versa. You have the context, and this context helps you to predict what should be in this context. So what are the details of these two approaches? So the continuous bag of words, so just to remind you that bag of words, the technique which is not purely NLP technique, so it can be used in different areas, in computer vision, for example. The bag of words is the multiset. Do you know what's multiset? Come on, multiset. How different from the set? So you can have multiple instances of the same object. So you have a bag of apples. For a set, if you put an apple and another apple and another apple, you will remain with a single apple. This is how the set works. You put apple multiple times, then the single apple remains in the set. For multi-set, you put 3 apples and 2 pears, and there are 2 apples and 3 pears in the set, without respect to the order of them. So, bag of words is a multi-set. You can find the applications again, so in working with images, text, and other areas of computer science. So what is the architecture? Architecture is very simple. You have the input, which is one hot context encoded, meaning that you have the vector, you take the window, which is controlled by a hyperparameter. So you have like context of 5 words, meaning that the word and 2 words of context to the left, 2 words of context to the right. And you do what? You encode the context by one-hot encodings, placing the numbers in the positions for these words. The output is the overall collection distribution, saying that, so for this context, what are the probabilities of words. And again, so the vectors are of the size of a dictionary, so they are wide vectors. So what we need to have a narrow hidden layer, which you can control. So you can say what number of dimensions you are interested in. And from this level, so I'm actually answering the question on the slide. From this level, you extract the embeddings. Okay, so you train the weights of these matrices and use this matrix to get the vectors. So again, the result is a matrix, so the same as we used previously, but instead of trying to compute the exact values of the vectors, we do what? We target the prediction of the word by a context. Okay, so this is the difference.
Well, input one of the vector is not contains the word, but only the points.
So what is one hot encoding? It's like the string of a turn document matrix, where ones are standing in the places of words. And the model is trained like this. So you take the window of like 5 words and you slide this window to the text, considering each composition of 5 words as context plus the word you are trying to predict. Um, So as I mentioned, so you can consider term document metrics as the form of writing down bags of words. Again, so you can find the connection here. And it found out that this approach and this approach, which is the let's say the brother of the previous approach, work very good. The other approach is continuous skip grams. Continuous means that you take continuous contexts. Skip grams mean you skip the word out of this context, and you are trying to maximize. So instead of predicting the current word based on the context, it tries to maximize classification of a word based on another word in the same sentence. So you place some a word and see what are the words should be in the context of this word. Increasing the range in both methods, in the continued bag of words and in skipgrams, they improve the quality, meaning that sometimes in our language the semantical connection can be like in a very large distance. In the method they encount this, so they can add decreasing weights for a distance. So the closer the word, the bigger the weight. But for that time, for 2013, training of word to vector was a computationally uh, expensive task, so they tried to avoid using the big hyperparameters, big values of hyperparameters. Any comments for this model? Again, so two approaches: predicting the word by a context, predicting the context by a word. And the architecture itself, so this one is from some slides. I grabbed it, but this one is from the paper. And again, the architecture is pretty simple. So you have this one hot encoding of a vector, narrow hidden layer, and so it's like very simple architecture. Not it's a shallow network, not deep network, but still for some reason it works. As a bonus for this, they got the vector space arithmetics. I think they also had it before, but the beauty was the following. So they grabbed some types of connection of concepts. For example, the plural form dog, dogs, cat, cats. And they figured out that for like, a large bunch of pairs of this type, the difference vector will be very similar. So it's like the arrow will be always looking like this. So for words with plural and singular form, their difference will be similar. Also, this works for like the say the profession and the type of like the gender, so king and man, queen and woman, and that brings us to very interesting situation. So when you can use some arithmetics if the vectors are aligned in the same direction, so you can um, subtract, for example, uh, so compute this difference. Yes, so between man and the king, you compute this difference of the vector, and you apply this difference to a queen, and it finds out that the closest possible vector in the latent space is woman. So you can use some mathematics to compute the concepts. I can say that if you make a step aside from the examples from the paper or from the examples from the website, you will fail. So most probably it works for only the some sample of words which are highly represented in the text and so on. But still, this was the beautiful uh, result. So what else can I say about Word2Vec as the model? So how did they train it and how did they measure the quality? So first of all, the idea was very simple. It was stochastic gradient descent. They use backpropagation, nothing, but no magic. It's how you usually train your networks. What was interesting, it was the task which was given for a model. Again, so you do something, you train the model in a supervised, unsupervised manner. So you take the text, and text is already a data set. You don't have to search for some targets to mark up the text. So, but why are you training this model? So, uh, what should be the purpose? And they stated two purposes in their paper. So, why did they train this kind of model? So, what kind of target it should optimize? And the first is the searching for closest synonyms, concepts which are similar, and maybe antonyms are also considered similar concepts. And this was the first task, to search for words which are similar to be replaced. And the second thing is to somehow fix this kind of vectors. So they wanted to actually infer this algebra. The target of all the experiment was to get this result. And this was not the happy chance, which they said that, wow, we got this arithmetics. But it was actually implicitly hidden in the state of the paper. Why it was implicitly hidden? Because all the tasks which they gave to the measuring of quality was, there were two types of tasks. First, they tried to measure semantic similarity, which was marked up by humans, saying that these two words are semantically close, these two words are semantically distant, and they want to increase this metric for this number of questions, or let's say phrases. And this one is for syntactic connections, as they were actually met here. So, for example, if you have the slides in your laptops, you can look at this. These are screenshots from the paper. They looked for the capital attribution, so Athens to Greece, Oslo to Norway. They looked for adjective to adverb, apparently, ethical, unethical, for opposite meanings, and different syntactic connections. Meaning that actually their target was to infer this kind of vector algebra. And what is interesting that all the data sets which are mentioned here, like this one new data set that they proposed in the paper, the MSR data set, and also the word similarity 353, they are all data sets inspired by Google. So the guys who implemented this paper that time worked in Google. The data sets were inspired by Google. And it doesn't mean, so I cannot say that result of the paper was inspired by metric or vice versa. So it can happen that they had some kind of data set, they trained the model, and wow, it works like this. So let's build the data set or let's build a metric which will emphasize this behavior, saying that we can solve these two types of tasks. But so you see that the method of training was unsupervised, but for measuring the quality of the network, they used particular tasks. Okay, so this is some kind of tricky thing, meaning that we cannot guarantee that the logical connection was not opposite. So they got the result on the network, and they decided to emphasize that how beautiful was the result. So this is my concern about the paper. But still, for those tasks, they compared them to other methods, and we see the significant increase of quality. And actually, in some tasks, they broke, like this coin barrier of 50%, saying that they became better than a coin. So semantic is, here you look at this higher part of the table and you see what is semantic connection, the currency. So real in Iran, I'm not sure that real is in Iran, but still it's currency is something. There are city and state, like Illinois and Chicago, Oslo always the capital connection. There are the semantic connections. The connection like first is a capital of second, and you try to measure that the network will produce you the same results as the phrases in the training set. Yeah.
processor was trained labeled by humans and later trained
So the model is trained in a unsupervised model as the autoencoder actually. It's the architecture. So the wide dictionary size layer here, dictionary size layer here, and the narrow layer inside. But the result of this training is bestly described by this kind of tests, and these tests are manually marked up by humans. Bless you. Okay, so these are my concerns about the method. And what should go next? So I want to again put an emphasis on some points about the word-to-vec problems and maybe some other models problems which present like for today. So first of all, out of vocabulary words, meaning that you train the model the words which are in vocabulary, and if you meet any word which is not in vocabulary, you don't know how to build the embedding for this word. This is the first thing. And second thing, that even if you look at the parameters of training the model, you see that as the number of data is big, you cut off the rarely represented words. So for word2vec, you will remove all the words which are in the whole data set underrepresented, like 5 or 4 words. It means that you cannot, with a guarantee, infer the vector which is good for embedding. That's why all these words are usually embedded in the same position in this space. So all the underrepresented words, they have the same vector. And this is the problem. So the similarity of two concepts which are very hard but rarely met will be the same. From the philosophy and from the chemistry, you'll get the same embedding for two concepts, which is it should be fixed with some sticks and stones when you put it in the production. And this, of course, works for any model, not only for word2vec, but it was mentioned here. Second, at least in the paper, they don't work with grammar, abbreviations, forms, and homographs. Do you know what's homographs? What is homograph? The words which are like spelled in the same way, but have completely different meaning. Like even if they have the different types of speech, parts of speech. So what are the examples? So the green as a surname and the green as the adjective. Yeah. Okay. So this was out of the scope of the paper, and of course you understand that for this kind of model, how it's designed, it will mix these words into a single concept. And second thing that, of course, in the paper there's no discussion about lexers, stemmers, and whatever we mentioned previously, saying that they don't even try to fix this problem. They just train it on the data. Again, still the training time depends on the numbers. This is just note that you will both depend on the context size and on the dictionary size, meaning that the bigger parameter you put, linearly you will grow the time of learning. Bless you. And still, this model only works for single words, as previously we considered the words as concepts in our LSA, latent semantic analysis. Here we have the same idea. Unfortunately, we can only build an embedding for a word. We cannot embed the longer snippet. What I can say that, of course, if you are an engineer, you will always find the way how to fix it. And averaging is one of techniques. And for example, I think in GenSim, which you will try today, I hope you all downloaded the dataset and library. And GenSim word2vec model allows to embed paragraphs. Actually, it uses averaging. So you can embed the text, and it returns the average vector. The problem of the average vector, you know that the longer the text, the averager is the average vector. It's closer to 0.5 in each position, meaning that it will be useless for longer text. For shorter text, yes, but only for short. So these are the discussions of word2vec. If you have any questions, you can either ask them right now or keep them until you read the Wikipedia article. So what are the other approaches? What was the next step? Next step was actually done by the same team of developers, by the Google team, and they said that, but what we need to apply this thing for search. Yes, so we are looking for some approaches to search the data. And single words are not solving our problem. They introduced the doc-to-vec approach, which was, I think, published in the same year or the next year. And the only brilliant idea they introduced, they took the text, split it into paragraphs, which of some length, and they said that the number of a paragraph will be somehow another word. So let's give a name to each of these paragraphs, and when we train the model, we do what? We embed in the same way we use 1,000 encodings for vectors of words, and also we have the paragraph vector, which is like first, second, and so on, the number of paragraph in the data set. Meaning that when you train the window on the same paragraph, you provide what? You provide the same number of paragraphs and the 1,000 encodings of sliding window of this bag of words. When you change the paragraph, you change the value here, and you continue. Okay? So a paragraph becomes some kind of a word which is present in any small context in your text. So the idea is very simple, but it allowed to infer another metric. So you remember that what we were looking for here. Sorry, I'm going forward. So we're looking here for this kind of metrics, which takes 1,000 encodings and bring them to the latent space of smaller dimension. Actually, what we're looking here for the same thing, but also we infer one matrix for here and one matrix for paragraphs. So actually, we're together building embeddings for texts and for paragraphs together. Okay? So the result is two matrices. Yes?
How can create a many pairs? You said only about the number of pairs. It's like we depend on the number of pairs, and if the text contains the same number of pairs, then it's the same text. Or it
I
doesn't.
didn't get your question. So can you repeat the question in a small number of words?
All you said was to many text depending on the number of pairs.
Mhm.
It means that if I have two texts with the same number of pairs, they are the same.
Oh, okay. So
Why do
we
the same?
consider the data set as the whole long text. This text is split by paragraphs. Paragraph is something which is from your interest. It can be a sentence, it can be actually a paragraph by /n, or whatever. So you said my text consists of paragraphs. This is the whole data set. So you have only one text. And you have like this number of paragraphs which is fixed by the very beginning of the training. So you do what? You take the vector of this length of number of paragraphs, which can be thousands, hundreds of thousands, and you use the same one for encoding for training. So you do the same tactics. You use a sliding window and train word to vec, but together with this, you add one more vector and you concatenate. Okay, paragraph, which is one hot encoded number of paragraph, and the one hot encoded words in the sliding window, and they are trained together to predict a word. Okay, and actually, what you have two matrices. One is responsible for paragraph, and the other is responsible for words. And as the result of training, you get the matrix which can map a paragraph to a small dimensional vector. Uh, the problem with this model, I think it's not that big, but still, the inference stage. So, okay, the purpose is that to give embeddings to paragraphs, but what if we face the previously unseen paragraph? What we can do? And so, and they said what? We add one more column to the paragraph. So we have one more paragraph here, one more dimension, and we use gradient descent to train this vector. So actually, the inference of the vector of the paragraph embedding for unseen paragraph is the training phase again. So it's time consuming. So it's not very cool to use in production. Still, this approach gave an interesting result. Again, they provided two approaches. The first approach is to concatenate the paragraph vector and the word vectors, like the vector with 1 hot encodings of words. Uh, and the second is ignore the context, so only the paragraph. And you do what? You take the paragraph number, you do 1 hot encoding, you sample a random window, and sample some random words from this window. And you try to predict that if you get this number of paragraph, you got these probabilities of these words. Again, unsupervised manner, you have the text, you take the paragraph, you sample some words from this paragraph, and you predict by the number of paragraph these words in the context. Both of them, again, can be parallelized, that's why it can be trained in some distributed systems. So the okay, so this one again, this model, which was on the previous slide, is trained by word to vector, so you put the context, and then you need the word in the context. The same vector. This is like the vector of the size of dictionary, of your vocabulary. How many words do you know? And you also add the concatenate this vector with the vector, which is 1 hot encoding of the number of paragraph, which can be considered as adding another word to the vector. So each paragraph is characterized by some concept. And you try to predict. Of course, this paragraph vector will influence the prediction of the words, meaning that in different paragraphs, this set of words will predict different words. Okay, so that's how the semantics of the paragraph is encoded. You hide the semantics in this paragraph vector. And the other approach is the following. So if you don't want to train as this way, you do what? You take the paragraph vector as an input to a network, just 1 hot encoding, and you try to predict some sample of words from this window in this paragraph. Not the whole paragraph, meaning that you don't put lots and lots of ones and zeros in the vector, but you limit the size. You say that I'm predicting 6 words. So I'm grabbing the random window, take 6 words from this window, and I'm trying to predict given a paragraph. So I trained this model, and I got something which is also predicting in this layer, predicting the semantics of the paragraph. Okay?
Why random window?
Not random. Window is, I think window is fixed, and the words are sampled randomly from this window. Because you need like 6 words for training.
About where?
Hmm?
I mean, words for describing paragraph.
Useless words. I think you should go for a paper. I'm not sure about how they process the stop words, but in this paper they did what? I think they used the whole set of stop words and whatever, and they even used punctuation marks as the full size words for training, meaning that the concept of paragraph can depend on the type of the sentence. It can be a question sentence, or it can be a statement. Again, they used stochastic gradient descent for embedding paragraph vector of unseen paragraph. Again, just note to remind you, they need to run training phase, and they used this particular model not for the general task, not for the task they used in Word2Vec, but for the other task. Okay, so the model is practically the same, but the task is different. Maybe because this task is solved okay with this model, and the model was a sentiment analysis. They had taken 5 class sentiment analysis and 2 class analysis, and compared their models with other models, and they got the best result. Of course, why should they publish if they got not the best result? So this was another approach. So again, so we evolved the model and got a beautiful result in some different area. Dr. Vec. So yeah, it's the Dr. Vec training and quality measurement. Do we need a break? Yes. Okay. 13, I think. They both, I think, in 2013. Okay, let's continue. Guys. The places. I have not very long ending of the lecture. I think we can finish even earlier. So, to sum up, we're now in the place where we created, like not we, but the team of uh, Google created the model, which is very simple in terms of neural networks, which can be trained in an iterative way by stochastic gradient descent. And anyway, it produces the matrix we need, which is the matrix of projection of one hot encodings into latent space. And the quality for some tasks, which they specify, of the syntactic similarity, semantic similarity, or sentiment analysis, they are better than for the methods which were before. Maybe this was because of nonlinearity added to the model. Who knows? Just one simple difference give us the quality update. So if you want to see the other architectures, you go for Glove, which was created practically at the same time and was used mostly in the same way for the same tasks. So again, the link for it for you. So what if we try to go deeper? What if shallow networks are cool, but still limit our opportunity to express the language? And in 2000, I think either 13 or 15, I can fail here, but you should go for a link to check. Microsoft, no one expected from Microsoft, but Microsoft published a paper about deep structured semantic model. What was their original architecture? They, first of all, they had a completely different approach to what is an input. Instead of just giving one-hot encodings of text, they gave us queries and headers. So some pairs, not the single, but the pair of concepts. And of course, this goes from the idea that Microsoft is implementing Bing search engine, and they want to predict paragraphs by queries and queries by paragraphs. Okay, so they need to build some model which will give them initial relevance scoring for you give the query into the search engine, you got a snippet of text which is the most similar to this query. And of course, they trained it for some metric which I will mention next. And instead of, so they trained to predict cosine similarity, so they had what? The architecture for a query, some deep architecture in the field of deep architecture. The output vector is 128, and the same architecture for a vector, also for a snippet. And again, so you got embedding here, so you can extract embeddings for text from these levels, and then you run cosine similarity, and you try to predict this cosine similarity of these vectors, where the cosine similarity is modeled by CTR. I'll mention. So what was important? Again, so initially this network had a purpose, as Word2Vec had a purpose to build the latent space arithmetics. DSSM was created to build matching between queries and snippets of text in the web pages. So they use it, of course, they use it for specific tasks, meaning that they will target the specific metric. Second, the problem. If we use a deep network, if you just multiply 300 by 300, you'll get what? 9 and 4 zeros. Okay, 90,000. Okay, and again, 300 by 128 and by 2, you get some pretty big number of parameters. And for this kind of network, this size of input vector, which is, and I'll figure it out. Sorry. Is very small. It's around 10,000 of values in the input vector. They used different approach. Instead of using a bag of words, they used a bag of 3 grams. What is 3 grams? It's 3 letters following one by one, met in the text. That's why you can do what? You can first of all encode the text, the word with some 3 grams, and it will be pretty the same. So few one-hot encodings in the vector. But second thing, they wanted to deal with typos right in the requests. So if you miss, for example, the double letter in the word, or if you replaced the single letter A by O, for example, in the word which you don't know how to spell correctly, it should not lead you to completely different word embedding. It should bring you to maybe you're making some mistake and only one dimension in the vector will be different, but others will be the same. So they use this letter trigrams again to focus on typos. They used it for search, and how did they train it? They used the following approach. As they trained it for search engine, they put a vector, this vector as an input, and for cosine similarity equals 1, which means similar, they used positive clicks. So meaning that you got the output of a search engine. If for this pair of query and the document, the human in the search clicked on the document, meaning that this is a correct match. So, but how should we look for zeros in this training set? So, what should be zeros? And negative was the answer was shown in the search engine representation, but not clicked. So this was 0. So cosine similarity 0, meaning orthogonal vectors. And this is not necessarily lead us to relevance, because of course, if you open any search engine, now you see that there are more relevant documents, less relevant documents, practically relevant, and totally relevant documents. That means that it can happen that the document which was okay, which was relevant, but just the second relevant document is considered as a negative example. And this one is not actually solving the problem they wanted to solve, to rank by relevance. Yandex, who obtained this model and saw an interesting perspective of using this model in the search, made some changes in this model. What were the changes? So first of all, Yandex team extended the input layer. Instead of just using trigrams, it also added an input vector of 1 million of one hot encoded words, so I mean the big dictionary of words, and also 1 million of most popular word bigrams like New York and so on. Assistant professor and I don't know, Nikita Bogomazov, whoever. Yeah, I know. Just for some reason I remembered him. um, so these are bigrams, most frequently seen. And now, instead of having 30,000 vector values, we have like 2 million of these values, 2 millions. Now you have the wider vectors. You can go with another depth. So instead of using 300, 100, 120, they swapped to 150 and 2 times 300. It means that in Yandex, if you talk to any developer who uses DSSM, you will always speak about 300 dimension vectors. DSSM mostly of this size. Sometimes there are small dimensions, but those models which are used for search, they are 300 dimensions. And what was the approaches to fix the problem with training? The first approach was to randomly sample negative examples. So instead of not clicked, just by randomly sampling examples, you train the model. And they made the model to predict this instead of predicting the relevance. Guessing what is the relevant instead of randomly select. So it's not, again, the ranking for relevance, it's ranking for zeros and ones. 1 for match and 0 for randomly sample, meaning that the model is deep enough to learn this kind of function. They failed on fake negatives. So they tried to build fake negative examples, and instead they got the network which was very good in guessing what is the fake sentence and what is the real sentence from the network, from the web. And so after failing these two approaches, they approached to hard negative mining. So what is this thing? You take the random best predictions and use them as negative samples again, and you repeat this procedure multiple and multiple times. And this approach, for some reason, worked. Yeah.
What is the random negatives?
Random negatives, or in the positives.
Random negatives.
First one.
Random negatives. Again, so you train the network to predict some number. So in the end, here, this network should give you the number. You do what? You are giving the input to predict some value. So in the training set. Okay? So what is the training set? The input is the text and the query, the pair, text and query. The output is some metric which we are trying to predict. Okay? And we say that, okay, we think that we are predicting assigned similarity. This is our task. We want to have what? To embed the query, embed the header, the text, multiply these two vectors from the last layer, and get 1 if they match, and 0 if they don't match. Okay? This is our task. But we don't know what's assigned similarity in the very beginning. So we should take some numbers which, from our perspective, are somehow similar to this target, to predict them. First approach, which was provided by Microsoft, they said, let's, for ones, so for this vector multiplied by this vector equals 1, we will take the fact that the person who used the search clicked on the document. Okay, click through. The other thing is that they tried different approaches. Again, random negatives mean that 1 is for click, 0 is for some random document. So here, here negative example was the document is shown on the search engine representation page, but not clicked by a user. That means 0. And it doesn't model relevance very well because it can be a relevant document anyhow, but you train it as 0. So they did what? Instead of using particular samples, they used random samples, saying that let's grab a random pair. For some reason, this query and this random header can be relevant, but in most cases, they will not. Okay? So in just majority of cases, they will not be single. Yeah? I think this is the terminological mixture because I grabbed these pictures from the Habra article, and they use this pair of terms to express the query request and some snippet of text. So actually, how this SAM is trained for search, you put the words from the query, like one hot encoded like this, and you put the words from a text snippet of a document embedded like this. And you try to
That's what you want to show.
yeah, in the search engine. Again, the question?
If you search G,
Yes. Yeah, but the case is different. So of course, this is supervised learning, and unlikely the Word2Vec, which was unsupervised.
and people at the end just checking if this document is relevant manually.
No. You can collect the data set for search engine in two ways. First way is to hire a person who will look with the eyes and mark the relevance of the document as relevant, non-relevant, and so on, and pay money for this. The second thing is that try to benefit from the users. And you do what? You just record down the log of actions of users in your search engine. So you have some, like say, the name formula. You're using inverted index. You use inverted index, you introduce the first version of your search engine. And these people who used your search engine, they clicked some documents which they considered relevant for their queries. And this is now my training set. And now I trained a completely different model using this data, the clicks from the users. And what Yandex ended up with, hard negative mining, meaning that your model is trained somehow to predict some metric, let's say click-through. Then you take random best predictions and then use them as negative samples, and you retrain the model again. And this leads you to some good result. This technique, they stated, is similar to GANs, but instead of GANs, where you have two networks competing for the result. One is faking, one is trying to guess what is fake, what is not. Hard negative mining means what? You have the same network fighting itself. Okay, it tries to bring the best relevant document to the top by uh, putting a border between the best one and some other random best.
Why? But how to say? Yeah, I see the like kind of best relations in symbols. Why I need to use is a negative symbols?
I think the idea was the following. So if you have some predictions, you take the best prediction possible, like the one which is most relevant, and some good predictions as negatives, just to be able to be sure that the best prediction will be always. I mean, I read through the article. I went through the article. Maybe you will read it and you will understand it better. But the idea was that they iteratively tried different approaches to training the network, and they failed. And for some reason, this one worked for them. I don't know what's the mathematics behind this, but sounds like they just were lucky in getting the good training approach for this particular network. Maybe someone who is working in theoretical machine learning can explain the theory behind, but at the moment, I just cannot guarantee that my answer will be correct.
Like a machine, you just try several
Data scientists, you know.
and it's something wrong, and next you go to the mathematics.
Yeah. And one important thing is that as Yandex was more experienced in search by that time, they said that click-through is not mandatory meaning the relevance. Click-through says that the person, for some case, interested by the header. And you know that there is a thing called clickbait. You can type some interesting header, which is totally irrelevant to the article, but for some reason you click it because it's like the beautiful kitty, or it's the way how to obtain 1 billion of rubles in 20 seconds, and you of course want to read this article. And it doesn't mean that they are relevant to the query. Just show more porn in the top, and you will get more click-through. So that's why Yandex introduced the other thing, the dwell time. Dwell time is when you go for a page and you remain there for some time. So you measure how long the user stayed. So if the user stayed there for a long time, meaning that the user found the information, which is interesting. And the dwell time is one of the metrics, and of course there are some other metrics exist. So again, much wider input vector holding the trigrams, words, and word digrams. Altogether, the width of this layer is 2 million of values. End of this also 4 million of values as an other set of depth of layers, particularly stated linear and non-linear layers here, and other target instead of cosine similarity dwell time. And they were successful. In 2017, Yandex launched a search engine based on DSSM model, which was called Korolov. I think it was a public launch, and they even got the session with the International Space Station because Korolov is, the one who made it possible to fly to the space. So this is the architecture which was used like at least 2 years ago. I'm not sure if it's used right now. I think yes. It's very hard to switch from architecture to architecture in a company of the scale like Yandex. So if you want to see something similar, so I'm recording. Yes, I'm recording. You can go for Ilmo and look for this neural network, which is appeared practically in the same time and solving the same idea. So again, just to be clear, that Word2Vec, the model created by Google, was targeting the unsupervised training and was good in some particular task in semantic and syntactic match and in sentiment analysis. DFSM was specifically created for search engines. That's why Yandex grabbed it from Microsoft, because the architecture, the idea was interesting, and it is now used in search engines. But still, you can use DSSM as the technique for word embedding for your other tasks. You can measure similarity. Why not? And now we go for BERT. I think for details, better read it by yourself. But the starting point is the following. Instead of setting the particular tasks to solve by the networks, the authors of BERT, they said, we will target of learning a language model. So not specifying the particular task. Not search, not similarity, not syntactic, not semantic, but the language model itself. And we will measure this by a multiple set of tasks. So we will train some kind of model, and then we will try to apply it for different tasks. For, let's say, sentence generation, for semantic match, for search engines. And we will measure how good this model in all of these tasks. So instead of going for particular question, they try to answer multiple questions. That's, I think, not the architecture itself, not the depth of the network, not the way how they build it, but the idea that we are not going to train the model for our purpose, but we will train the general purpose model for language model. I think yes. Train a silver bullet.
But actually, which tasks work
What?
which tasks work best?
Good question. I think that they claimed something about the natural language generation, but maybe you will fix me. But what was the best task for
I
Bert?
think they made all NLP tests. So basically, they one good general model for understanding language itself, and then you fine tune it for smaller tasks, and it just gives the best results.
Yeah, just the best one. And the mode of search was pretty similar. So we return back to word to vec, and I think that the idea was somehow taken initial idea. The idea was the following: so we have the sentence. We take the sentence and we mask out 15% of the words in this sentence, and put in the mask the keyword there. And we train to predict the words which are missing. That was the way, which is very similar to the continuous back of words. Okay. Of course, it was also trained to predict logical connections between phrases, meaning that not only the single phrase was used to train, but also the sequence of phrases. The architecture was, which was taken, was a transformer. I think you should know this. I'm not the very good at this, but this is kind of architecture which is instead of just using some kind of recurrent neural network, it can propagate the values from the encoder layer, not only on the next decoder layer, but also to the further layers. And they also, I think this is very interesting fact, that they returned back to the roots, saying the following: instead of considering the language as for LSTM for other networks, which were predicting the next word in the context, they said let's consider bidirectional context. Again, as in word to vec, instead of looking only forward, we can take the context from the future and train the context, the overall context for predicting the word. Meaning that the idea is again back to roots to the word to vec approach. Use the context which is in the past and in the future. Train the network. And I think that's all. If you want to go deeper in BERT architecture, because I don't think that I'm first of all that proficient that I can easily explain you how it works. But the second thing is that this is not the mandatory part for us. But also, I want to mention that this is what now state of the art. You can download it easily, find the trained models for different languages, and you can use it for your tasks of search, prediction, classification, whatever, for free. No, for computational power, let's say. And if you want to read and understand different ideas behind the methods, what were the weak points and strong points, you can go for the papers, which are either linked in the slides, or they are attached to Moodle, so you can find the papers there for all these networks. Thank you very much. I think that's all. So I finished a little bit earlier. Thank you very much. Yes, the questions are welcome.
How long do they train? It's very weak model. Like
I think the progress looks like this. Anytime you invent a new cool model, it is trained for a long time, let's say weeks or days or whatever, in some distributed context. And the Word2Vec was the same heavy network as BERT 7 years ago. And everyone said, oh, Word2Vec is very hard to train, it's very heavy network. And now you train it in what?
Limited resources.
But in your case, you can download the pre-trained network
And fine.
and fine-tune it if you want, or just keep it as is.
The initial model from 2018, we say that Google said it took for one GPU 400 days.
So 400 days for one GPU.
100 billion primes.
100. So to mean that they had much more GPUs, much less time. Okay. So Google can afford this. Yes.
So I'm sure who created
I think Google. Google again.
Initially, but then there are other people like
so the coder push results from but also
I think the architecture of the network. I'm not the theoretical machine learner, but I know that this kind of architecture is called transformer. You know that you have encoder layers, and then you have connection not to the next encoder node, but to others. In the context
which
layer.
is stacked well transformers on top of each other with just attention layers with extra.
So Nikita can explain it. You can ask Nikita.
Second blend.
Second one. That's obvious. You know, everyone knows it.
Huh? Several neural nets. Transformer is like attention net. The attention you will need, stack well on those.
it would be more complicated structures like
Просто очень большая рыба.
Nikita failed to explain. Okay. If you have any other questions, you're welcome. If you don't have any questions, you have a break for I think 20 minutes and come back to follow the tutorial.
What is the meeting today in research review? And what people that do not do research review should attend this meeting?
Я записал в эту группу.